Hello, today we're going to be talking about converging and diverging lenses. These are also often referred to as convex and concave lenses. These are just different names that they're often referred to as, and you're probably going to need to know both of them. You can tell it's a convex or converging lens by the way it's shaped. Usually it'll be thinner at the bottom and then thicker in the middle. And a concave or diverging lens is opposite of this, with it being thicker on the bottom and thinner in the middle, as you can see in this picture. Every lens has two focal points. These are used when drawing the lens to make it easier. And the focal points are going to be the same distance from the center of the lens on both sides. However, when you're doing calculations for a convex lens, you're going to always use a positive focal length. So F is always positive. And then for diverging or concave lenses, you're going to always use a negative focal length. So F is always negative. So if you can just remember this, it'll make your calculations very easy. And so on your equation sheet, there's two equations that you need to know to figure out converging and diverging lenses. One of these equations is 1 over F equals 1 over distance of the object plus 1 over the distance of the image. So usually they'll use O for the object and I for the image that it creates. And we'll see this in the other equation we need to know to find the magnification. And that equation is the magnification equals the height of the image over the height of the object. And this also is the same as negative distance of the image over the distance of the object. So if you have the height of the image and the height of the object, you can find magnification. Or if you have the distance of the image and the distance of the object, you can also use that to find magnification. So we're going to run through a couple quick practice problems to help us make sure that we fully understand these lenses. And the first example we're going to do is for a convex or converging lens. So we're going to say that the focal length is equal to 8 centimeters. So this distance right here is going to be 8 centimeters. This is the focal length. And then we're going to do the distance of the object. So we're going to draw an object right here. And this object is going to be a distance of 10 centimeters. And then finally we're going to do the height of this object. The height of the object equals 3 centimeters. And so we can use this to find the distance of the image, so where the image will be produced, the magnification, and if it's going to be upright or inverted. And I'm going to walk us through that. I'm going to show you how to do it just by doing some calculations. But we're going to start with this equation right here. And we're going to do 1 over F, which is 8 centimeters. 1 over 8 equals 1 over DO, so 1 over 10 plus 1 over the distance of the image. And to solve this equation, it's pretty simple. I'm going to show you how to do it. It's kind of hard because they're all fractions. But if you just multiply all the fractions by the denominators. So it's multiply everything by 8 times 10 times di. So if you multiply 1 over 8 times 10 times di, this is going to cancel. And this is going to cancel, the 8. So you're just going to be left with 10 di. And then if you do 10, the 10s are going to cancel. So you'll be left with 8 di. And then if you're doing di times 8 times 10 times di, you're just going to get 8 times 10, which is 80. So this is the equation that you're left with. 10 di equals 8 di plus 80. Then it's really easy to solve. You just subtract 8 di. Subtract 8 di. So you have 2 di equals 80. And this is centimeters. You have to remember that all these measurements are in centimeters. So 2 di equals 80 and then if we divide by 2, we get DI equals 40 centimeters. Okay, so because this number is positive, 40 centimeters is positive, it means it's going to be right of the lens. It's going to be on the right side of the lens. So our image is going to be somewhere over here at a distance of 40 centimeters. So that means the image that is projected by this lens is going to be 40 centimeters away from the center of the lens. And then we can calculate the height of the image using this equation up here, and we can figure out the magnification. The magnification is going to mean how much bigger or how much smaller our image is compared to our object. So to do that real fast, I'm going to erase a little bit so we have a little more room right here. We're going to do magnification equals negative distance of the image. So we know the distance of the image is 40. So negative 40 over the distance of the object. Our object distance is 10. So you get magnification equals negative 4. So if your magnification is negative, it means it's going to be upside down. It's going to be inverted. So our image right here that is being projected is going to be upside down, and it's going to be negative 4, so it's going to be 4 times bigger. So originally the height of the object is 3 centimeters, so 3 centimeters times 4 is 12. So this is 3 centimeters, and this is going to be 12 centimeters. But we have to remember that because it's negative, it's going to be down in the negative direction. And so that's how you can find the magnification, and how you can use this equation to find the height of the image. So the height of the image equals negative 4 times 3, where the height of the image equals negative 12 centimeters. So I'll make this negative because it's just to help us remember that it's in the negative direction. So that's a simple way to figure out the image that is being projected by this lens from this object. And we're going to do another example that's pretty similar, but we're going to do it with a concave lens. So with a concave lens, we're going to get a little bit different numbers so we can see a different example, and we're just going to walk through it. So we're going to say f equals 4 centimeters. But we have to remember, because it's a concave and diverging lens, it's going to be negative 4 centimeters. So your focal length right here is going to be 4 centimeters. The distance of the object is going to be 8 centimeters. And the height of the object, we're just going to keep it at 3 centimeters. So just as an example to draw it out, the distance is going to be 8 centimeters. So this is going to be 8 centimeters. And we're going to have this is going to be 3 centimeters tall, 8 centimeters away from the lens, and this focal length is going to be this one over here, which is negative 4 centimeters. So that's all we need to do to solve everything we need to find out about this lens. So we just do the same thing. 1 over f equals 1 over the distance of the object plus 1 over the distance of the image. So 1 over f is 1 over negative 4, and that equals 1 over 8 plus 1 over di. And then we can do our fancy denominator trick. So do negative 4 times 8 times di. So 1 over negative 4 times this is going to leave you, the negative 4s are going to cancel, and you're going to be left with 8 di equals 8. The 8s are going to cancel on this next one, so you're going to get negative 4 di. And then for this one, the di is going to cancel, so you're going to get negative 4 times 8, which is 32. So you're left with 8 di equals negative 4 di minus 32. So to solve this, we can just add 4 di to both sides, and that gives us 12 di equals negative 32. So now we know that 12 di is going to equal negative 32. So if we just divide by 12, we get di equals negative 2.666, or 2 2/3. And since di is negative, it's going to be on the same side. The image and the object will be on the same side. So it's going to be, let's say, so this is 4 centimeters, so 2.6 is going to be about right here. And we'll draw that out so you can remember. 2.66 centimeters. We have to remember this is in centimeters. Okay, so this is where our image is going to be. And then to figure out if our image is going to be upright or if it's going to be inverted. Because our object is upright, but our image could either be upright or inverted. We're going to use this equation up here. M equals negative distance image over distance object. So I'm going to clear a little bit of room. I'm going to just erase this right here. And then show you how to do it. So M equals negative, and then our distance image negative 2.666 over the distance object is right here, which is 8. And so that we can use that to find the magnitude. And let me put that into my calculator real fast. Which is going to give you, and let me look, that's a harder, math to do. But if we just use a calculator right here, it'll make it easy. 2.666 divided by 8, and that gives us 0.3325. So 0.33, so the negatives will cancel and get 0.33325. So this is about like 1/3. We can just round this to 1/3. So the magnification is going to be 1/3. And so positive magnification means, like I said over here, if the magnification is negative, it's going to be upside down, but if it's positive, it's going to be right side up. So we're going to have an object that is 1/3 the size of this. So if we use this equation, the height of the image, so 1/3 equals the height of the image over the height of the object, which is 3. And so if we just solve for hi, we're going to get hi equals 1. And so the height of the image is going to be 1 centimeter. So this will be 1 centimeter. And so that's a basic intro into lenses. And this is just 2 examples with each lens so that we can get a good feel for them. And then just the 2 simple equations that you need to know. And so this is just an intro. There's obviously more stuff that you can do with this. You can do problems where there's an image and it's projected through this lens, and then it's projected again through this lens. So you have to do 2-step calculations, but really it's simple. You just take the image over here and just plug it into the next equation. And so it's not that much more complicated. You can just use this basic understanding that you already have to figure it all out. So thank you for your time. I hope you enjoyed it. If you have any questions or comments, please feel free to contact me. And thank you.